So let's start with, let's just go right into an example and we'll see the biggest, we're going to make one big assumption that's going to make solving this a lot more straightforward. So we're just going to kind of construct a scenario where we know some of the potential. And so I'm going to do my best to draw this carefully. So let's say I have the y-axis here and the x-axis here. And I have basically some metal sheets that we've kind of welded together. So let's say I have a sheet right here. Let me color this to blue here. Let's say I have one metal sheet that kind of goes off in this direction. So that metal sheet kind of keeps going, and it also kind of comes towards us as well. And then I have another metal sheet that's kind of underneath it like this. Something like that. Is that, hopefully that's clear what I'm trying to draw there. So I have two sheets. One of them is at y=0. And the other one is at y=a. So one of them's kind of flat on the ground and the other one is kind of shifted up at y=a. So these are two infinite grounded planes. Right? And so as soon as we say grounded tells me that I know v is equal to 0. So everywhere on this blue sheet, the potential is equal to 0. However, these two sheets are connected by a small piece that goes from y=0 to y=a at x=0. So kind of everywhere in between here, the best way to think about this is like, it's like the cover of a book. The top and bottom of the book are these metal sheets, and the spine of the book is this insulated piece. And so we have an infinite strip of insulated material connects the sheets at x=0. And so at that point, at x=0, because it's insulated, so remember, insulation means that the charges aren't going to move around. They're not going to do anything special. And so that whatever potential is on that green section, it's going to stay that potential, and the charge isn't going to say move over to the blue sheets. It's just going to, everything is going to stay exactly where it is. And so for this example, let's say that the potential of the green strip is a constant. And we'll just call it V0, just some constant, whatever it might be. It could be 20 volts if you like, whatever your favorite voltage is. My favorite voltage is 9 volts because of the battery. So we have this sort of setup here, and our goal is to find V as a function of x, y everywhere in the region between these metal sheets. Okay. Any questions about that? It's just a setup. Does that make sense? Awesome. Okay, cool. So the first thing I want to do before we start jumping right into this differential equation because the boundary conditions were so important for the method of images, the boundary conditions here are going to be very important as well. And so I just want to spell out what the boundary conditions are, and we'll keep that in mind as we start working through solving the differential equation. So let's summarize our boundary conditions. So whenever we're thinking about boundary conditions, we want to kind of think about how many boundary conditions we need. And the best way to think about that is if we look at our differential equation over here, the Laplace equation, we have two derivatives with respect to x and two derivatives with respect to y. And the number of derivatives is sort of a hint that tells you how many boundary conditions you need, right? Whenever I take an integral, an indefinite integral, I need an arbitrary constant, right? And so the same kind of thing applies here. I have two derivatives, which means I'm going to have two arbitrary constants for x, and two derivatives, which means I need two arbitrary constants for y. And we figure out those arbitrary constants with the boundary conditions. So there's two derivatives of x and two derivatives of y. So I need two boundary conditions on x and two boundary conditions on y. Okay? And so all that means is that I need to know something like, I need to know v of something comma y, right? It might be x equals 0. I need to know v of x comma something. It could be y equals 0, y equals a, and that's what we're going to kind of work out. So let's start with our boundary conditions on y first, because that's going to be that's going to sort of make a little bit more sense. So what I want to know is, what is v as a function of x? So we're going to figure out what it is as a function of x. But what boundary do I care about for y? There's going to be two of them. So what's one boundary that I need to know about for y? If we look at 0, right? We definitely want to know, or we do know something about the potential at y equals 0. And according to our problem, we said that it's an infinite grounded plane at y equals 0. And so v of x comma 0 is 0. So that's one of our boundary conditions. What about the second one? If we got y equals 0, we also need one at
y equals a.
Y equals a, exactly. So that's the other boundary for y. And again, that's a grounded plane. So we know x at the potential at y equals a is 0. Notice it doesn't matter what x is, right? These planes go off to infinity, so it doesn't matter what value of x I have. All that matters is I have these two boundary conditions where y is a specific value, and I know the potential at that value. Okay, so these are our two y boundary conditions. But now we need some conditions for x. So I have v of something comma y. It doesn't matter what value of y I'm talking about. But again, just like we had here, I want x equals 0. And so at x equals 0, that's referring to that green strip along the kind of spine of the book cover there. And so that green strip we said is specifically set to v0. And not v6, v0. So it's a constant. Okay, so now this one's a little tricky. I'll let you guys think about this for a second. I need another boundary condition on x, right? Where is my other boundary for x? Where could I have, like, clearly for the y, it was clearly the two blue sheets. That was like the start point and the end point for y. The start point for x is x equals 0. Where's the end point for x? Where's that going to live?
Would it be infinity?
Yeah, there you go. Infinity, right? Since those sheets go on forever, the only place that I really care about what the potential is doing is as x approaches infinity. And again, it doesn't matter what value of y we have, it approaches infinity. And so from all your other stuff with calculating potential, you're probably used to the fact that when we go really far away from stuff, the potential should be 0. So when we're really far away, we know that we should get 0. And so those are our 4 boundary conditions. We have 2 boundary conditions for y, because I have 2 derivatives for y. I have 2 boundary conditions for x, because I have 2 derivatives for x. So that kind of gives you an idea of where I should pull these boundary conditions from.